COVID code quality controversy. Corporate coding community creates copious concerns causing quite quarrelsome kerfuffle. Today on Craft versus Cruft. I'm Ray Myers, and I've been programming professionally full-time for about 12 years, and I am not a scientist. However, I was for a time trained as such. My wife has defended a doctoral dissertation. I have some exposure and some degree of respect for the rigor that it takes to truly add to human knowledge and to refine human knowledge and in some cases to correct human knowledge. So the question we're going to look at today is, should scientists who code well? Is it important that they do? To what extent does that affect the validity of their results? Is it even feasible for them to use best practices? And we're going to use a pretty interesting and topical example from recent history. In April of 2020, the Imperial College COVID-19 response team in London, led by Neil Ferguson, who would come to be known as Professor Lockdown, produced what is known as Report 9. In this, they predicted that without government action, 500,000 deaths from COVID would result in the UK and 2.2 million in the United States. This research has been considered critical in steering Prime Minister Boris Johnson and the UK government in general to change their course with respect to addressing the pandemic. What brings us to talk about it? Well, the findings in Report 9 were created using, you guessed it, software. Now, we don't know, without the lockdowns and various other measures that have been instituted, how many deaths there really would have been. Something we do know is that in the United States, with the measures we did take, however imperfectly they were implemented, there were absolutely copious measures taken. There were nonetheless over 200,000 deaths. You can find this code online, at least a version of it. There's a program called COVIDSIM. It was adapted from some code they'd been tinkering with since circa 2005 for studying the behavior of flu pandemics. In fact, you give it different parameters based on the certain aspects of how the disease spreads, and it can model situations regarding different diseases, just with different input parameters. Kind of interesting. The version that was originally used to produce the report has caused some controversy. That version was, by all accounts, a single 15,000 line C file. We don't know exactly what it looked like. We've seen a heavily improved, cleaned up version, but some people who have seen it have had not such great things to say. Bugs that they corrected over the course of cleaning it up. So this has led a lot of people to be very critical of the fact that these really high stakes policy decisions, involving instituting lockdowns that have tanked economies, to some degree, would be trusted to some possibly horrible bug-ridden code. There was an anonymous Google employee that published a few articles criticizing the methodology of this, for example. For instance, the lack of modularity, the lack of any unit tests or other automated tests, the stochastic nature of the simulation, stochastic meaning that you incorporate randomness in a simulation. Now that, if done properly, I think is actually totally valid to do, so an odd criticism there. For a while, the GitHub issues of this project were flooded with people's complaints and comments, people demanding all work based on this code be rescinded. People just, this is the worst thing I've ever seen, Possibly some of these people had a political axe to grind, perhaps didn't want the measures and were looking for any way of attacking how those things were brought about. A lot of these criticisms didn't show much scientific literacy. For instance, there's an assumption that, okay, this could be buggy code and this one model produced this one output, and therefore the entire, emerging scientific consensus about this is wrong. Like, even if the code was perfect, a model doesn't have to be right. Models aren't always right. Like, you always have to look at them relative to the other information you have to see how much you want to trust a particular model in a particular context. They've all got assumptions they rely on. One of these assumptions is, in this case, that the code doesn't have bugs that markedly affect the result. One article that I think, sums up what the normal rebuttals are was by Phil Bull, who's a cosmologist in London. That article was called "Why You Can Ignore Reviews of Scientific Code by Commercial Software Developers." Now, Phil Bull seems like a pretty good guy. We had an amicable exchange, and it is a well-written article, despite the fact that I don't agree with all of it. I don't want to mischaracterize him, so you can check out the fullness of what he wrote, but this is his own summary from the top. It's not my summary, it's his. Many scientists write code that is crappy stylistically, but which is nevertheless scientifically correct. Following rigorous checking, validation of outputs, etc., professional commercial software developers are well qualified to review code style, but most don't have a clue about checking scientific validity or what counts as good scientific practice. Criticisms of the imperial COVIDSIM model from some of the latter are overstated at best. So were some of the criticisms overstated? Yes, absolutely. And were they not informed by some of the points and others that I mentioned about, how do they really know this is correct? They've got more ways than you've thought about to check their assumptions here. However, I sense this defensiveness goes a little too far, saying, style, quality, these things don't matter to correctness. This aesthetic we have of code being, neatly organized really just doesn't have any place in the scientific community, is what is tantamount to saying, I think. And I'm sorry, no. Quality's a thing. Quality matters for correctness, right? One of the things that we achieve when we unit test and we refactor is that the bug rate plummets. We can continue to make modifications to code with much greater confidence. It's never perfect, but much greater confidence that we aren't breaking it. So of course, being able to lower the number of defects, places where the code isn't doing what it's intended to do, would matter in producing a scientific result, especially one that was going to lead to very important policy decisions. What else? Readability. Things are broken down into discrete chunks with inputs and outputs and not in big blobs that modify shared state. All of a sudden, very much easier to comprehend, easier for other people to get into the code base, especially if these parts are named very well. Why do we care? Huge teams won't need to maintain it, right? It's research code. Well, yeah, but by its nature, then it needs to be peer reviewed. People need to be able to assess the validity. So you're telling me it doesn't matter if the thing that they're assessing, is it all possible for them to comprehend and have confidence that it does what it says it's doing? Of course not. Of course you don't think that. Now he argues that, there's only so many hours in the day. There's only so much these researchers can be experts in. They're not going to be experts in all the aspects of software development. But I think you're underestimating how much you can get done with the fundamentals. If you're at the level where you're putting, 200 and 500 line functions there into a 15,000 line single source file, you really, don't have to do much learning and practice to get a lot better than that. Give me 2 days and I will show you how to get, much, much better at this. And this won't slow you down as you develop this code and maintain this code. These are things that speed you up. My response to Phil: I think if you've got one group that knows about code quality, which does indeed relate to correctness and ability to peer review, but doesn't know about the science, and another group that's vice versa, what's needed is more understanding between them and not less. So I would urge commercial developers to be more patient and constructive than some of the feedback I see. Someone coming in with, this is bad code, I have no specific suggestions, haven't found any specific bugs, haven't read any of the papers, and don't know how it's being used but it's bad, isn't going to make any headway. That's not helping. That's just trying to poke holes. I would also urge anyone writing scientific code to learn a little bit about refactoring, unit testing, descriptive names, modular design. I realize there are only so many hours in the day, but these skills would make you more productive and help you collaborate. And like any comment thread, duck and cover, don't know what to expect really. I kind of forgot about it, came back to it later. Phil actually left me a really thoughtful response, saying among other things, yes, I do think that adopting some professional software engineering practices would be useful for a lot of scientific code. And our bigger projects, we use unit testing, modular design, descriptive names, etc. He also mentions an effort that I was unfamiliar with called software carpentry, where someone's packaged a bunch of fundamentals on software design, version control, various pragmatic stuff specifically for scientists. Great. Now he also says, but what I want to do is separate scientific correctness from code quality because in his experience, they're not tremendously correlated. I guess I get off the train there, but I probably define quality a lot more broadly than he does. Fellow using the handle dguest also responded to the comment thread saying, there's a little too much polarization here in the dichotomy he had been drawing between you're either academics who know science or you're politically motivated code reviewer doing a hatchet job. Because you look at the role of John Carmack in this situation. Now, he was the author of Doom and Quake, right? Very well-known industry coder. Before the code came out, John Carmack helped review it, helped fix bugs, helped clean it up. Was one of the people using his time to help be constructive about this. Then a lot of people cherry-picked some of his remarks during that process and tried to turn it around into an attack. As this was unfolding, there was another fortunate development, which is that a group called CODECHECK was able to reproduce the findings of Report 9. What CODECHECK does is they simply take the software that was used in some study. They independently run it themselves, documenting how they did it. They put that out. Here's what was the same. Here's what came out a little different, and found and certified that the principal findings that came out of that simulation as used in Report 9, they were able to verify. And that's using the cleaned up, debugged version of the code that was released publicly. So those findings were not, solely reproducible by some hidden version of the code that may have some horrific problem that hasn't been looked at. So what do we pull from all this? Well, the situation here was pretty typical of what you call research code. When I was close to done with school, I remember talking to my capstone teacher about some code that he was working on for a conference paper. Actually, it was a really cool idea about using evolutionary algorithms to produce the harmony that would go with a sung melody. Oh, that's really cool. I said, have you thought about releasing this code? And he said, well, I wouldn't want anyone to see this. It's probably got all kinds of memory leaks and whatever. And there's something very odd to me of you're going to publish this paper about this thing, but the code itself you wouldn't want anyone to see. I don't doubt the validity of his results, but that was kind of bizarre to me because I'm like, you guys are the ones teaching me how to code. That is no less weird to me now than it was then. I think I understand a little better what was going on. Code quality is not taught in such a pragmatic way. They talk about designing something right. So if I was going to have this be better, my only option would be to write it completely from scratch with a new design of exactly how the classes are going to be laid out now. What you call predictive design. And of course, you're not going to do that as you go because, when you're putting together a research prototype, you throw a million things at the wall. You're copy and pasting. Eventually you get some, oh, okay, I can run with this one. By that time, do I want to rewrite it all? No, I gotta write my annotated bibliography or something. But there are other options besides predictive design. There's what's called reflective design, right? Where you change an existing design incrementally to get closer based on your observations of what your pain points specifically are. There's refactoring, improving and refining the design of existing code. There's techniques for bootstrapping testability when you don't already have it, if you haven't designed for testability out of the box. There's a lot of tools you can have in your toolbox here. And I think it would take a relatively low level of investment to be able to regularly produce code that you actually don't have any reservations of publishing right alongside your paper. So at the end of the day, I think between the software industry and the scientific community, you've got two sets of groups that could learn a lot from each other. I've talked about a few of the things that they could learn from us. By all means, please contact me and let me know how I can help if there's any way. You can reach out to me on LinkedIn or @LambdaApocalypse on Twitter. I've also included in the description Phil Bull's Twitter information. Phil, I hope I did you justice here. Thank you for a very interesting and productive exchange that we briefly had, and for helping to inspire me to make this video. You don't always see a situation where sides of different perspectives are honestly having a conversation with the goal of bridging the gap and establishing a shared understanding. These days it's kind of refreshing. I wish you all more of that. The word university and the word universe, I'm told, derive from one truth. There is not your truth and my truth. There is the one truth we are trying to discover. On the opposite token, I think there's a ton that professional software engineers could learn from scientists. When you see the way we often develop opinions, make, in some cases, very high-stakes decisions, sort of based on who shouts louder with the more compelling argument, is relatively rare that we'll make these decisions with anything approaching scientific rigor. Notable exception might be the book Accelerate by Nicole Forsgren, Jez Humble, Gene Kim. They establish certain practices of continuous delivery and DevOps have not only a correlation but a determined causation of certain aspects of organizational performance. We should see more of that. That's the exception rather than the rule. So I think that about wraps up this week. We've got some great topics coming up. Sarancha Morningstar has requested an episode on the role of QA. Nathan at Salesforce has requested a couple topics, including investing in developer tooling and breaking into DevOps track as a junior level engineer. Also hoping to announce a collaboration coming up with Elevated Agility Labs, an emerging Caribbean consulting startup. Look out for that. Keep the suggestions coming, and remember what Lao Tzu said in the Tao Te Ching: I have just 3 things to teach: simplicity, patience, compassion. These 3 are your greatest treasures. And he also said, with patience, the most tangled cord may be undone. Thank you.